Hello everyone. In this video, we are going to learn finite automatons in a very simple way. Okay? So please don't think this topic is very difficult. Just because the word look technical, right? So we will take it like a classroom explanation. Don't worry about the topic of finite automata. First, we will understand what a finite automata is doing. Then we will see DFA, then NFA. After that, we will learn how to convert NFA into DFA. Okay. The main idea is very simple here. Okay. Machines reads input symbols one by one, like zeros and one or A and B. So based on the symbols, it move from one state to other status. At the end, it stay accept or rejected. So in this full videos, just keep four words in the mind: input state, input state, transitions, and final results. Yeah. Uh, let's let's see. Okay. So before going to into DFA and NFA, let us first ask one simple questions. Okay. So why do we need study finite automata? So in computer science, many times we need to check whether an input follow a pattern or not. For example, in compilers, when we write a program, the compiler has to identify the tokens like identifiers, keywords, number, and operator, right? So it cannot simply guess. It needs a clear checking method. So finite automatas give that method. Okay, just it's checking the clear method, right? So you can think of it like pattern checkers. uh, we give some input strings. The automatons need it symbols by symbol. After reading full inputs, it give one answer, whether it can be accept or reject. So even though the diagrams look small, the idea is very useful in compiler designs and many other areas also. So to make the ideas even easier, imagine vending machines. At first, the machine is in ideal state, right? That means it is waiting. When we insert a coin, it move to the other states. Maybe coin receive. Okay. So then we press a button. It move to the other states and give drinks. So here, state means current situations. This is the same idea in finite automata also. The automata may be Q naught now. After reading the symbol 0, it may move to Q1. After reading the next symbol, it may move to Q2. Okay, so don't treat state as a complicated word here. State simply means where the machine is currently standing, and, and or what situations the machine is currently in. Okay. Now, in textbook, finite automata is usually written in five parts. You may say Q, sigma, deltas, Q zeros, and F. But let us not memorize it blindly. Q means collection of states. Sigma means input symbol. Okay, like zeros and ones. Delta means a transaction rules which tells us where to move. Q0 is a state symbols. F is a final state. Now in diagram, these things are very easy to use. The circles are the states, the arrows are the transactions, and the arrow coming from outside shows the start symbol, start stages. Okay. The double circles or marked stage shows the final stages. So whenever you see automated diagrams, don't panic, just identify these five things one by one. State, input symbol, transaction, start symbol, final stage. Okay. Now let us start with DFA, deterministic finite automatons. The word deterministic simply means fixed and clear. In a DFA, if a machine is in one state, right, and it read one input symbol, there must be exactly one next status. For example, from Q naught, if the input is 0, it should go to one fixed places. If input is 1, it should also go to one fixed places. So there should not be a two choices for the same input. Okay. Also, we should not leave it blank. So DFA is like a roadmap where every signal has a clear directions. Because of this, DFA is very easy for compilers to run directly. Okay. So because at every steps there is only one possible Moses. Okay. Hope you understand. Okay. Let us take a simple DFA examples. Okay. We want to accept all binary strings that ends with 1. So if the last symbol is 1, the string should be accepted. If the last string is 0, it should be rejected. Okay. So here we use two stages. Q naught means the last symbol is not 1, or we have not yet got at 1 at the end q end. Okay. So q1 means last symbol is 1. Q1 is a final. Now see the movement. Okay. From q naught, if we read 1, we go to q1. If we read 0, it, we stay in q naught, right? Okay. From q1, if we read another 1, we stay q1 because the string still ends with 1. But if we read 0, we go back to the q naught. So the state is remembering only one useful things is what the last symbol. Now let us trace the inputs 101. Using the same DFA, this is an important part because many students understand the diagrams but they got confused while tracing. So don't do it slowly. We start at Q1. First symbol is 1. So from Q1 we go to Q1. So from Q0 we go to Q1. Next symbol is 0. So Q1 we go back to Q0. The last symbol is 1. So from Q0 we go to Q1. Now the input is over. We check the current state. It is Q1. Q1 is a final state. So the input 101 is accepted. That is all. Okay. We are not checking the input is one shot. We are checking it step by step, symbol by symbols. So let us see NFAs. NFA means non-deterministic finite automata. In simple word, NFA is more flexible than DFA. In DFA, one input from one status has exactly one next status. But in NFA, for the same state, the same input, we have multiple choices. Sometimes there may be a no move also. Sometimes we may even move without reading any input. So that is called ellipse epsilon transaction. At first, this may too confusing, but the accepting idea is very simple. If at least one possible path reach a final state after reading the input, so then NFA accept the string. So NFA is like a saying, try all possible path, and if any one of the path is succeed, it will get accepted. Next, let's compare DFA and NFA side by side. Okay, so this comparison is very useful for exams and also for understanding. In DFA, each state and input there is exactly one move. In NFA, there can be a 1 or many moves. DFA does not allow choices. NFA allows choices. So DFA does not have epsilon transactions, but NFA can have epsilon transactions. In DFA, the machines follow one single path. In NFA, machines may have many possible paths, but one important point: both DFA and NFA have the same power. So that means whenever long range and NFA accept, some DFA can also accept the same languages. This is why we learn NFA to DFA conversions. So look at the NFA examples. From Q naught for input A, there is two arrows. One arrow goes to Q1, another arrow goes to Q2. In DFA, this is not allowed, okay? But in NFA, it is allowed. So when input is comes, NFAs can think of both possibilities. One path goes to Q1 and one path goes to Q2. Now, if Q2 is final, okay, if Q2 is final state, then one possible path has reached the final state. So the input can accept. So the input can be accepted. Okay. So this is the main beauty of NFA. Okay, it is not saying only one road is possible. It's saying many roads may possible, and if any successful road exit, the string is accepted. Okay. Okay. So now the one questions may comes. If NFA is acceptable, why do we convert into DFA? The reason is practical. Okay. NFA is often easiest to design because we can give choices. But when a computers run in machines, it is easier if there is only one next step. So NFA gives exactly that. It gives one clear transaction for every stages and input. So the common process is this: we may first create an NFA because it is simple and compact. Then we convert it into DFA so that it can be executed in a straightforward ways. Very important points after conversations. The language should not changes. So the DFA must accept exactly the same strings that NFA accepts. Okay. Okay. So the main idea of NFA to DFA conversion is this. In NFA, at a given time, machines may have more than one possible current state. For example, after reading some input, the NFA may be able to stand Q0 and Q1 together. So depending on the different path, now DFA cannot stand into two separate stages at the same time. So what do we do? We create one DFA stage that represents its sets of NFA states. For example, the DFA states may be written as a Q0 and Q1. This means this is the original NFA. Possible states are Q0 and Q1. So this method is called subset construction because each DFA states is a subset of NFA states. Here is a step for conversions. First, it starts with the set contains the NFA start state. If the start state is A, okay, then the first DFA state is set of A. Second, for every input symbols, find where we go from all the states inside the state. The third, whenever you get a new state, add it, yeah, add it as a new DFA status. Fourth, Fourth, repeat this process for every new stage until no new subset appears. Fifth, make the final state. Last step is very important. If a DFA states contain at least one final state of NFA, then DFA states become the final. So conversion is not magic; it's just a table filling process done carefully. Let us do one conversion examples. This is the most important part of the video. So watch slowly. We have a three NFA. We have three NFA states: A, B, and C. There are three NFA states. Okay. Okay. The input symbols are zeros and one. The input symbols are zeros and one. The start state is A. The start state is A. The final state is C. Okay. The start state is A, and the final state is C. Okay. From A on input 0, from A on input 0, A and B. A and B. Okay. From A, from A on input 1, we go to A. Okay. From B on input 1, we may go to C. Right. Other moves are empty. Our job is to create a equivalent DFA. This means DFA should accept the same string as this NFA. We will not rush. We will start from the start status and create subset status step by step. Okay. First step. We start the DFAs with the set of A's because A is the start state of NFA. Now we find the transactions of set A. Okay, for input 0, look at the NFA tables. From A on 0, then if we go to A, right? Okay, and go to A and B. So in the DFA tables, from set A on 0, we write A, B. For input 1, from A, the NFA goes to A. So from A on 1, we write A. So now we check whether any new subset has appeared. Set of A is already there, but a set of A and B is new. So we must create a new row for A, B. Okay. So this is how the tables grow gradually. Okay. So now we process the new DFA states set of A and B. This means NFA may currently be in A or B. A or B, right? A or B. So when we calculate the next move, we must consider both A and B. First, take 0 from A on 0, we get set of A comma B. From B on 0, we get empty. Okay. Combine them, the result is set of AB. So from set of AB on 0, write set of AB. So now take input 1. From A on 1, we get set A. From B on 1, we get C. So combine them and we get set of A comma C. So from A comma B on 1, write A comma C. Now A comma C is a new subset. So add other row for it. Complete DFA tables. Now we process AC, A comma C. We combine the move from A and C for input 0. From A we get A comma B, and from C we can get empty. So the result is A comma B. For input 1, okay, for input 1, from A we get set of A, and from C we get empty. So the result is A. So now look at the tables, the states where state we have our set A comma B and A comma C. The transaction also going only to the exiting stages. New states, new no new subset is coming. So the table is complete. Now mark the final status. The original DFA final state is C. So any DFA subset containing C become final. Okay, here A comma C contains C, so A comma C is a final state in a DFA. Okay. So once the DFA table is completed, drawing the diagrams easy. Every rows in DFA tables become one state in diagram. Okay. Uh, so we draw A comma B and A comma C. A is a start symbol because it's come from the NFA status A. So AC is a final state because it's content C. Now we can now we add transaction using the table from A. Input 0 goes to AB, and the input 1 goes to A, right? So from AB, input goes to AB, and input 1 goes to AC. From AC, input 0 goes to AB. Input 0 goes to AB, and the input 1 goes to A. So the table is our guide. So don't draw by guessing. Always draw by the complete tables. Okay. Okay. It is quick recap. Everything. Finite automation is simple machines used to check whether the input strings follow the patterns or not. Okay. So DFA is remedies. So for each stage, and input symbols, there is exactly one next state. Okay. uh, NFA is non-deterministic, so it can have 0, 1 or many possible next state. NFA accepts a string if at least one possible path reach a final state. It converts NFA to DFA. We use subset constructions. That means each DFA state represents a set of NFA states. Start with the start state subset, fill the tables for each input symbols, add new subset, continue until no subset appears. Okay, and finally mocks final state properly. So that's all for this video. So practice two or more, two or three conversions problems, and then this topic will become very comfortable. Okay, so thank you guys.